Hello, students. Welcome back. We are in our energy chapter, and now we are going to learn about heating, cooling curves. This graph I have here for you is the heating, cooling curve for H2O or water. So let's look at the parts of the curve, this graph. First of all, we have the y-axis, which is temperature. In this case, it's degrees Celsius, temperature. The x-axis is going to be heat that we add as we go along this curve. Heat is, of course, represented by Q, and the unit is joules or kilojoules in this case. Let's start at the origin of this graph, the corner, where the temperature is as low as it can be and we don't have any heat. So think about what would exist when we're really, really cold and we have no heat at all. Would we have a solid, liquid, or gas when it's really as cold as it can be? You are correct if you said solid. So we're going to start in the corner of this graph here. Look at my cursor with a solid because we are cold and we don't have any heat. And now what we're going to do is start to add heat as we go across the x-axis. Well, as we add heat, the temperature will go up. So the blue line starts to go up. As we add heat, we increase the temperature. We add heat, we increase the temperature until eventually what will happen to a solid as you heat it up? It will start to melt, right? So eventually we'll reach the melting point. That is what is over here on the y-axis, MP, melting point. And for ice, the melting point is 0 degrees Celsius. So now we're at this point between the blue and the red line. That point, we are switching from region 1 to region 2. Once we start melting, the solid turns into liquid. So we are melting. So we have a solid liquid mixture. It's a mixture of two phases, solid and liquid. And we are melting the solid, melting the solid, melting the solid as we go across the red line, which is flat. The temperature does not increase during this. All the heat goes into breaking those intermolecular forces holding the solid together so we can turn it into a liquid. Okay, so we do not raise the temperature when we're melting. It stays at the melting point, so it is flat right here. Eventually, all the solid is melted and we have 100% liquid. That is this point here where my cursor is. At that point, we have a liquid. So as we add heat, we are heating the liquid and the temperature goes up again. So we're heating the liquid, heating the liquid, heating the liquid, heating the liquid, and the temperature is rising and we are on this blue curve. Eventually, if you heat a liquid enough, what happens? It will begin to boil. Yeah, so that's why we have reached the boiling point, BP, on the y-axis, which for water is 100 degrees Celsius. So now we're switching from region 3 to region 4, where we are turning liquid into gas because we're boiling. So we have a liquid gas mixture. So we are boiling the liquid, boiling the liquid, boiling the liquid, and that is the red flat part. And we stay at the boiling point because all of the heat we're adding goes into breaking those intermolecular forces. We have a liquid and we're pulling the liquid apart into gas. So all the heat energy goes to that. So it stays flat and the temperature stays constant at the boiling point. Eventually, we have turned 100% liquid into 100% gas. So now we have a gas again, and we're going from region 4 to region 5. We have a pure gas. We're adding heat to the gas, so we're heating the gas, and the temperature begins to rise again, and this just continues to go up. So that is what a heating cooling curve looks like, a heating cooling curve. It has 5 regions. Regions 1, 3, and 5 are the states of matter by themselves, solid, liquid, and gas. Regions 2 and 4 are mixtures where we are melting and boiling. All right, I hope that makes sense. You should be able to draw one of these on your own. Heating, cooling curves, very important in this chapter. For each region of the heating, cooling curve, we can calculate the heat needed given the information for the system. So we're going to do some calculations. For regions 1, 3, and 5, the heat is calculated using Q equals ms delta T, which we've already seen. Right? We've already seen Q equals ms delta T. So here it is again. Q is heat, M is mass in grams, S is specific heat capacity. The units are joules per gram degree Celsius. And delta T is the temperature change. It is always final minus initial. When you see that triangle change, it is always final minus initial. And it needs to be in degrees Celsius because specific heat is in degrees Celsius. So we're going to use the equation Q equals ms delta T and solve some problems now. Here we go, example 1. Calculate the amount of heat absorbed in joules to heat 5.712 grams of water from 25.0 to 38.9 degrees Celsius. The specific heat capacity for water is in a chart, right? It's in your textbook as well. You can look it up. It is 4.184 joules per gram degree Celsius. So we're going to use Q equals ms delta T. See if you can solve this problem yourself real quick. All we're doing is plugging in. Hit pause and solve. Okay, we're back. We have Q equals ms delta T. M is mass, which is 5.712 grams. S is specific heat capacity, which is 4.184 joules per gram degree Celsius. Temperature change is final minus initial, which is 38.9 minus 25.0 degrees Celsius. Make sure you do that subtraction first or put it in parentheses, then multiply by the other numbers. Grams cancel, degrees Celsius cancel. We're left with joules, and the answer is 332 joules because we need 3 sig figs based on our temperature only having 3 sig figs, right? Go with the least. Okay, so doing Q equals ms delta T is very important in this chapter. You will see this again on your exam and probably the final. Q equals ms delta T. Let's try another one. Calculate the amount of heat absorbed in kilojoules this time to heat 750 grams of iron from 25.0 to 38.9 degrees Celsius. The specific heat capacity for iron is 0.451 joules per gram degree Celsius. Q equals ms delta T. Go, you got this. And we're back. Let's look at our solution. Q equals ms delta T. Mass is 750 grams. S, specific heat capacity for iron, is 0.451 joules per gram degree Celsius. Temperature change is 38.9 minus 25.0 degrees Celsius. Grams cancel, degrees Celsius cancel. We have joules, but it asked for kilojoules. So you can either get your answer and then convert or put the conversion in the problem. I just put it in the same problem where we're going to convert from joules to kilojoules. Remember, kilo is big. So 1 big kilojoule contains 1,000 joules. The kilojoule is big. So because we have joules on top, we need joules on bottom. 1,000 joules in 1 kilojoule. Joules cancel out. Our answer needs to be 2 sig figs because 750 grams has 2 sig figs. So we get 4 1.7 kilojoules. Again, you need to be able to do Q equals ms delta T problems. You will see them again on your exam and the final probably. Q equals ms delta T. All right, good job. See you in the next video. Bye-bye.